Okay, so let's finish up section 5.3 of the book. We may not finish it all in one video, but certainly in two. Enthalpy, as you already know, is a thermochemistry or a branch of chemistry that's called thermochemistry, and it deals with thermodynamics. And basically, substances have potential energy stored in them in bonds, and so we can then use that energy to either release energy, or we can store energy in another compound. So we can either have the enthalpy positive or negative. If it's negative, that delta H is being released. If it's positive, it's being absorbed. So you don't need to know about internal energy other than a definition. Internal energy is the sum of the energy as heat and the work done by the system. When you go into AP chemistry, if you do, we'll talk about work there. And this is the first law of thermodynamics, which states that the internal energy of a system is equal to the work that has been done on the system plus or minus the heat that flows in or out of the system. And any other work that is done on the system. And this was by a physics professor. So it's a restatement of the conservation of energy law. I'm really not interested that you understand internal energy, but you do have to be able to calculate Q for various things. And so if Q is negative, it is releasing energy or releasing energy in the form of heat. If it's positive, then it absorbs energy. And so absorbing heat would be endothermic and releasing heat is exothermic. And so here's just another way of saying that same thing. But we are, again, only interested in the left-hand side of this picture. We are not looking at the right-hand side as of yet. So we're going to skip over work and here, but we do need to talk about a state function. And a state function is something that does not matter how you got from point A to point B. It is independent of path. And so it can be calculated many different ways. It only depends on the initial state and the final state, but not how that state was reached. So if I go from point A to point B to point C, the state function of that traveling would be just from A to C. So altitude or elevation is also a state function. So if you were on this mountain, I know I couldn't just drive straight up because it's too steep of an elevation. But what does happen is you go back and forth to get from the summit. But from the base to the summit is actually an elevation difference, and it doesn't matter how you got there. So enthalpy. Again, we're not going to worry about U, which is internal energy, or anything else. We're just going to calculate enthalpy changes, which is different than total enthalpy. So when we talk about enthalpy, we're just going to look those values up in a table and do calculations from them. This makes it a convenient way of determining heat. Since it's a state function, we don't have to worry about how we got there, but we can just calculate values. So, thermochemical equations. When we balance a thermochemical equation, we must use the product. In this case of this equation is H2O is a liquid, which would be its standard state at 25 degrees Celsius and 1 atmosphere pressure. Hydrogen needs to be in its standard state, which is a gas, and oxygen is also a gas. However, we can only form 1 mole of H2O as a liquid, and so we have to use fractions to balance this equation. So it has to be for just 1 mole of that product. And so this would be a thermochemical equation because it has not only balance for 1 mole of the product, but also has a delta H value associated with that. And the 1 per mole is left off because the equation is written just for 1 mole. So if I need to multiply this equation by a factor of 2, then I would multiply delta H by 2. If I needed to divide by 2, I would divide delta H by 2. If I were to And this makes it an extensive property, means it matters how much I have of it. If I were to reverse the reaction, then I would have to reverse delta H. So here we have the thermochemical equation on the top for making liquid water, and on the bottom we have for making gaseous water. And so we see that there is a difference there of about 46 kilojoules. And so we could then put those two equations together in such a way as to, well, here we've got, as we're making water, it's an exothermic reaction because delta H is negative. If we take water and we decompose it into its elements, then it's an endothermic reaction. And I can actually show you that one in class if you would like. So here's an example problem. I think we've done a number of these already, so we're not going to go through this. Standard state just means it's a commonly accepted set of conditions used as a reference point for the determination of the properties under certain conditions. IUPAC says that the standard state for a thermochemical reaction is 1 atmosphere, and solutions would be at 1 molar, and the temperature should be 25 Celsius or 298.15. So you'll often not see 298 written. You'll just see the little 0 at the top, which means standard state. So the enthalpy process for many types of chemical reactions and physical processes are available in reference literature. Basically, you're going to look it up in a table. And delta H is always for 1 mole of that product. So standard enthalpy of combustion, often called the heat of combustion, is when you take exactly 1 mole of a substance, you burn it with oxygen, and you form the products from that. For hydrocarbon, the 2 products are always carbon dioxide and water. So here's an example of doing the combustion of ethanol. Delta H for that reaction is negative 1,366.8 kilojoules for 1 mole. If I were to give you a number of grams, you would take the grams, convert it into moles using molecular weight, and then use this delta H as another conversion, and that would be negative 1,366.8 kilojoules divided by 1 mole, and that would allow you to cancel out moles. So here are some values that you could look up in a table. Nothing real exciting here. They would just be values you would look up. And again, same thing for these. We would have them in a table. I do not expect you to memorize any of these numbers at all. The only thing to note that is of value here is that each one of these reactions is written for 1 mole of that hydrocarbon or alcohol. So we know that hydrocarbons burn with a lot of energy, and that's really all this picture is trying to show you. So here we have the combustion of gasoline is highly exothermic process. Let's determine the amount of heat produced by burning 1 liter of gasoline. So it has a density of 0.692 grams per milliliter. So we can get from liters to grams using that conversion factor, and then we would use delta H from that equation. So we would first convert from 1 liter to 1,000 milliliters. Then we would multiply by the density, making sure that the grams canceled. Then we would use some molecular weight of C8H18 to convert from grams to moles. Once we get to moles, then we would use the kilojoules for 1 mole to get us a value of negative, and that indicates energy is being released, of 3.31 times 10 to the 4th kilojoules. That's a lot of kilojoules. So kilocalories or calories are what we use in all sorts of biological processes as well. And we can use all sorts of processes to do that. Again, you've done these kind of calculations. If you're making a particular compound, you have to use the elements to make the compound. So in this case, it would be carbon solid plus O2 gas would give me CO2. Heat of formation of that I can look up in a table, and there it is. This is the standard enthalpy of formation for carbon from it, or carbon dioxide from its elements. Elements are always zero, so you will not find any values for carbon or oxygen in this kind of data table. So we're going to skip that. We've talked about Hess's law. And Hess's law is kind of interesting because it allows us to predict a heat of reaction for something that we haven't done before and get an idea whether energy is going to be released or if it's going to be taken up, so that we don't have it get really, really hot and maybe blow up during a reaction. So it is, if a process can be written as a sum of several stepwise processes, the enthalpy change of the total process will equal the sum of the enthalpy changes of the various steps. And to do this, we just have to take equations or reactions. We may have to flip them. If we flip it, then we'll change the sign. We may have to divide or multiply by a constant, and we would do the same to delta H for that reaction. So here's our process. I have two steps that I can write for this. I can write the formation of carbon monoxide and this formation of carbon monoxide to carbon dioxide. We have a little issue on our formatting there. And so the net change, and we can get the values out for the reaction we're looking for. And then we would take those values and we would add them together, and that would give us our delta H for this reaction. So here's kind of a visual map of what's going on. If we start with certain values and we know what delta H is to go from CS plus O2 to get to CO plus half a mole of oxygen, and then we can then convert that into CO2. And so it would just be the differences between the two reactants and products. So here's basically the idea, that delta H of a reaction is equal to the sum of the products delta H's each time by their number of moles in a balanced chemical reaction, minus the sum of the delta H of formation for each reactant, each of those multiplied by the number of moles in their balanced chemical equation. So here we have this reaction, 3 moles of NO2 gas plus 1 mole of H2O liquid yields 2 HNO3 plus NO2 gas. What is delta H for this reaction? You could go to your book to Appendix G, and you would look for each of those substances, and you have to pay special attention to the state of matter for each. So NO2 has to be a gas, H2O has to be a liquid, it can't be a gas, etc. And so you would look up each of those numbers, and we're going to start with our products here on the top line. And since we have a HNO3 here on the top, and it has a 2 in the coefficient, so we're going to take 2 times the value for that, which is negative 207.4, plus 1 mole times NO, which looked up at the back would be this number here. And we continue on. Once we get all the values in, we add them all up, we get delta H for this reaction. So that finishes the chapter 5 notes that you'll need. Hopefully over the weekend I will post one for chapter 10. Thanks. See you in class.